Now let's go through the same process for an object that is slowing down instead. Based on what you saw for speeding up, I would like you to make a prediction about what the position time, velocity time, and acceleration time graphs will look like for an object that is slowing down and eventually coming to a stop. Pause the video and see if you can make a prediction now in your notes. I know that for an object that's slowing down, its velocity is going to go from some positive value to 0. And I know that the slope of the position time graph is the velocity or speed of that object. So I know that my slope here will go from some positive slope to 0. I can represent that with a curve like so. I'll show the tangent line again in blue. I have some positive slope. It becomes less positive, even less positive, until eventually it flattens out and we get a slope of 0 here. That's how I can be sure that my speed is decreasing here, because my slope is also decreasing. And eventually, if I come to a stop, my slope would be 0. So when it comes to the velocity versus time graph, again, I'll think, well, the slope here was some large positive, then it was some, medium positive value, a smaller positive value, and then eventually to 0. So on my velocity versus time graph, again, I'll represent that as the y values, right? Transposing that here. So I start off at some large positive, and then as time goes by, I end up less positive, even less positive, until eventually I actually come to a stop, so I end up here at 0. And I'll show that like so. So again, we have a linear relationship, but this time it's this is a negative slope. And the negative slope indicates that I am decreasing my speed, essentially. Every second, my velocity is decreasing, right? And so this also indicates, right, a negative acceleration. By slowing down, I'm essentially accelerating in the opposite direction. So if I'm traveling in the positive direction for my velocity vector, then this means my acceleration must be in the opposite direction, right? It's causing me to slow down. And so on my acceleration versus time graph, I can show that with a negative acceleration. I'll have to extend my x-axis here, or my y-axis, and show a negative acceleration down here. This is some negative value. Because, again, the object is slowing down, and we typically represent slowing down with a negative acceleration to indicate that the object is speeding up in the opposite direction, essentially. So this is what an object slowing down would look like. Let's take a look at perhaps one of the most complex examples we can, an object that changes direction. Let's say that you take a ball, a tennis ball, and you throw it straight up in the air, and you watch it slow down before it comes to a stop just briefly, changes direction, and then speeds back up as it approaches your hand and you catch the ball. So what you've got here are 3 different segments of motion, essentially. An object slowing down, coming to a stop, changing directions, and then speeding back up on its way down. How might we represent that with a position time, velocity time, and acceleration time graph? Again, I would like you to pause the video here, and based on what we saw for speeding up and for slowing down, see if you can come up with a prediction for each of these 3 graphs in your notes before proceeding. So again, assuming that our initial position is 0, we can combine what we saw for slowing down and speeding up onto our position versus time graph here. So as the tennis ball rises and reaches some sort of maximum point, it slows down, right? As it leaves your hand, it's traveling fast, but as it continues to rise, it slows down. And we can represent that with a curve like this. We'll stop right here. And so right here, the object has stopped. So the slope here is equal to 0. The ball has stopped for a moment. Now, after it stops, right, doesn't stop for very long, it continues to fall now, and as it comes back down, it speeds up on its way back. And so I can show that with that speed up portion, like so. Okay, now let me show you, let me prove to you why this is speeding up with the blue tangent line. So again, I have my tangent at some positive value, less positive, 0. And now I am negative, more negative, and then very negative, right? So this is some sort of large positive, it goes to some small positive value, becomes small negative, and this is a large negative value. And remember, all of these are our velocities, right? Our slope is our velocity. So what this tells me is I have a positive velocity that eventually goes to 0. And what that means is, again, I was moving in the positive direction. We're going to call this positive here. And then I stopped and started to change directions and move in the negative direction. And even though the slope is becoming more negative, I want you to think about the absolute value of the slope, right? It's becoming more like 1, essentially, and less like 0. So it is increasing. And so I can show this as speeding up, but traveling in the negative direction. Okay, so this is another form of speeding up. Now in my velocity time graph, I'll show that again with the red here for the y value. So the slope, right, slope here becomes the y value on my graph. So that was very positive, medium positive, small positive, eventually becomes 0, right? But keeps going, negative, and even more negative. And I'll connect that again with a linear relationship here. So something interesting happens here. Right here, the velocity changes direction. And as long as I'm up here in this region, right, in this positive region, this is traveling in the positive direction, right? Because my velocity is positive. But as soon as I stop, right, I hit some 0 velocity, so the ball stopped moving. It doesn't stop for long, though. It continues to travel at that same rate of change in the negative direction. So all of this represents moving in the negative direction. In this case, we're just going to call that down. So I represent a change in direction as actually crossing the x-axis on a velocity versus time graph. Now, again, the velocity versus time graph's slope here, so the slope of this graph is going to be the y value here, right? Our slope is our acceleration. And we haven't learned this yet, but we've observed that for any object falling freely through space on Earth, the acceleration on that object is a constant negative 9.8 meters per second squared. Again, the negative just means that it pulls it downwards. And so as we know, gravity, which we'll talk about later, gravity is a force that pulls objects towards really the center of the Earth. And so we see that as an object falling, but it speeds up as it falls, and it does so with a constant acceleration of negative 9.8 meters per second squared. We're going to call that g, but we'll get to that later. So there we go. We have the most complex situation we could have, an object slowing down, changing directions, and then speeding back up on its way down. So please now begin the matchmaking activity on Canvas to practice all of these graphs through many more examples and really hone your graphical analysis skills.